Okay, we're going to carry on today Chapter 9, Field Effect Transistor Amplifiers and Switching Circuits, specifically Section 9.4, the Class D Amplifier. Class D Amplifier on page 454. Just want you to underline again the sections that I have done. As usual, the introductory paragraph for the Class D Amplifier. Introductory paragraph says in Chapter 7, Class A, Class B, and Class AB amplifiers were introduced. Those types of amplifiers are generally implemented with either BJTs or field effect transistors. The Class D amplifier, however, primarily uses only MOSFETs. The Class D differs fundamentally from the other classes because its output transistors are switched on and off in response to an analog input instead of operating linearly over a continuous range of input values. All right, let's have a look at the block diagram of a basic Class D audio amplifier in figure 925. And see, here's my input signal. Here's the input signal. Then the first section that we're going to discuss, they are all discussed separately in the textbook, is the pulse width modulator. Then the second one is going to be the complementary push-pull switching amplifier. And then lastly, the low-pass filter before my signal reaches the speaker. All right, so I want you to underline, as I have done here in my book, Class D amplifier. In a Class D amplifier, the output transistors are operated as switches instead of operating linearly as in the Class A, B, and AB amplifiers. Switches, of course, what do I know about a switch? Switch is either on or a switch is either off. No? So it's conducting fully saturated or it's off. There's no conduction. All right. All right, let's see how this works. The major advantage in audio applications is that a Class D amplifier can operate at the maximum theoretical efficiency of 100%, compared to a Class A, which was 25%, if you can recall, and a Class B or AB at 79%. In practice, the efficiencies over 90% can be achieved with the Class D. Of course, theoretically, 100%. But nothing works 100%, so there are some losses and so forth, but it is very high. It's above 90%. All right, then the block diagram, as we've seen in figure 925, consists of a pulse width modulator, which we're going to discuss. We're going to discuss each of these components separately. Driving the complementary MOSFET output transistors operating as switches here in the middle, and then it's followed by a low pass filter lastly before my speaker. Most Class D amplifiers operate on dual polarity power supplies. We will have a look at that just now. The MOSFETs are basically push-pull amplifiers that are operated as switching devices rather than linear devices as in the case of Class B amplifiers. But anyway, let's discuss the first component there, the pulse width modulation, as in the block diagram. Pulse width modulation, please underline that first sentence. Pulse width modulation is a process in which an input signal is converted to a series of pulses with widths that vary proportionally to the amplitude of the input signal. Now this is illustrated in figure 926 for one cycle of a sinusoidal signal. Notice that the pulse width is wider when the amplitude is positive and narrower when the amplitude is negative. The output will be a square wave if the input is 0. All right, so just to recap what they've said there in figure 926, for my input signal, the sinusoidal signal, and you can see here As the sinusoidal signal moves into the negative section, I can see as it becomes more negative, these pulses becomes narrower. And as it becomes more positive, then I can see the pulse width becomes wider again. All right. Pulse width modulation. All right, let's carry on page 456. Page 456, top. The pulse width modulated signal is typically produced using a comparator circuit. Now, a comparator circuit is only discussed in chapter 13, and you will only see it again in theory in electronics 3, but they give us a basic explanation, as I've underlined there as well. A comparator, please underline there as well. A comparator has two inputs and one output, right? Op amp. There you can see is my comparator. It's an op amp circuit. You will do op amps in electronics 3. You can see it's got two inputs, positive and a negative. And then of course there's the output on the right hand side. Anyway, the input labeled with a positive sign is called the non-inverting input, and the input labeled with a negative sign is the inverting input. So, when the voltage on the inverting input exceeds the voltage on the non-inverting input, the comparator switches to its negative saturated output state. When the voltage on the non-inverting input exceeds the voltage on the inverting input, the comparator switches to its positive saturated output state. See that again here in the figure. Remember we said here, as the signal goes negative, there's my modulating waveform, that square wave waveform, and there I can see it switches to the negative state. Every time now as it becomes more negative, I can see it switches for longer periods, and then as it becomes more positive, I can see again that the pulse width on the positive side now becomes bigger, as it corresponds there with the sawtooth waveform that is applied there as the modulated waveform. All right. So the comparator just below figure 927, the comparator inputs are typically very small voltages in the millivolt range, and the comparator output is rail to rail. Now the rail to rail, what does that mean? It means that the positive maximum is near the positive DC power supply and the negative maximum is near the negative DC voltage. All right. So the voltage is applied on this circuit here. I think in the example there as well, there's the voltages applied to this device. Say it's plus 12 volts, minus 12 volts. Of course, the difference there, or the voltage range there, is 24. Now, minus 12 and plus 12, the range is 24. So the comparator will switch the voltages to close between the 24. Now, it cannot go exactly up to 12 volts, just below 12 volts. All right. So that is that rail to rail means, I say yes, I also underlined here, an output of plus minus 12 volts or 24 volts peak to peak is not unusual. From this you can see that the gain can be quite high. What is the gain again? Output voltage over the input voltage. Now, so for example, if the input voltage is 10 millivolts peak to peak, the voltage gain is going to be 24 volts peak to peak divided by 10 millivolts peak to peak, which is 2400. But since the comparator output amplitude is constant for a specified range of input voltages, the gain is dependent on the input signal voltage. If the input signal is 100 millivolts peak to peak, for instance, the output is still 24 volts peak to peak. All right, so the gain is going to get influenced. So now the gain is only 240 instead of 2400. All right. Frequency spectra. All non-sinusoidal waveforms are made up of harmonic frequencies. The frequency content of a particular waveform is called its spectrum. Now, we're not going to go into detail about that. What is important, though, is that the frequency of the triangular waveform must be significantly higher than the highest input signal frequency, so that the lowest frequency harmonic is well above the range of the input signal frequencies. I want you to underline that. But anyway, just to get back to the frequency spectra, when the triangular waveform modulates the input sine wave, the resulting spectrum contains the sine wave frequency F input. If you can look on figure 928 at the bottom of the page there. There it is. Plus the fundamental frequency of the triangular modulated signal FM and the harmonic frequencies above and below the fundamental frequency as indicated here. Those harmonic frequencies are due to the fast rise and fall times of the pulse wave modulated signal and the flat areas between the pulses. A simplified frequency spectrum of a pulse wave modulated signal is shown in figure 928, as we can see here. But please underline that last sentence, that is important, that I've said there, the frequency of the triangular waveform must be significantly higher than the highest input signal frequency, so that the lowest frequency harmonic is well above the range of the input signal frequencies. Otherwise, I'm not going to get the output waveform that I want. All right, that was the first section of this block diagram of my basic class D audio amplifier, the pulse width modulator. Now we're going to discuss the second section there, the complementary push-pull switching amplifier. You should be familiar with this, some of this theory as we've discussed in the previous chapters. The MOSFETs are arranged in a common source complementary configuration to provide power gain. We can see here in figure 929, common source configuration. Each transistor switches between the on state and the off state, as we have established already. It's either on or off. It's not operating linearly. And when one transistor is on, the other one is off, as shown in figure 929. When a transistor is on, there is a very little voltage across it, and therefore there is very little power dissipated, even though it may have a high current through it. When a transistor is off, there is no current through it, and therefore no power is dissipated. The only time power is dissipated in the transistors is during the short switching time. Power delivered to a load can be very high because a load will have a voltage across it nearly equal to the supply voltages and a high current through it. All right. So, as we can see here at the bottom, just below figure 929, you can see that the efficiency was 100%. But please mark that last paragraph as well, where it says, in a practical case, each MOSFET would have a few tenths of volts across it in the on state. There is also a small internal power dissipation in the comparator and triangular wave generator. Also, power is dissipated during the finite switching time, so the ideal efficiency of 100% can never be reached in practice. But as we've seen earlier, it's well above 90, which is also very high. All right, that was the second section. The last section then in our block diagram of figure 925 of the basic class D audio amplifier is the low pass filter. On page 458, the low pass filter, please underline that first paragraph. The low pass filter removes the modulating frequency and harmonics and passes only the original signal to the output. The filter has a bandwidth that passes only the input signal frequencies as illustrated in figure 930. So we can see in figure 930 there, remember we've done frequency response of amplifiers in chapter 10. Basically what happens there, filter cutoff frequency. So what do I have in the end? The signal flow shows, figure 931 shows the signal flow at each point in a class D amplifier. Small audio signal is applied and a pulse width modulated to produce a pulse width modulated signal at the output of the modulator where the voltage gain is achieved. The pulse width modulator drives the complementary MOSFET stage to achieve power amplification, and the pulse width modulated signal is then filtered and amplified audio signal appears on the output with sufficient power to drive the speaker, as in figure 923. 931, sorry. Figure 931. There we can see the whole thing. There's my small audio input signal, my 3 stages there. The modulator, there's the pulse width modulated signal, complementary push-pull where I get my power gain. With the pulse width modulated signal again, and then of course the low pass filter gets rid of the unwanted frequencies, and I have lastly my amplified audio signal, as you can see, amplified from my input signal. So class D amplifier, that's the complete class D amplifier. Then this concludes then section 9.4. As you've seen, mostly just theory that you have to know, some of those block diagrams and signals and so forth. Only 2 problems related to this section, but please read through it and make sure that you understand the basic operation of a class D amplifier.